Good morning, everyone. How are we doing today? Happy Wednesday. So I hope everyone's doing well. And so we'll kind of finish up our chapter 4 today. And then, of course, ask questions if you're here. And then also looking ahead to next week. So just a reminder, I should probably send out an announcement about this. But next week is midterms. And so I will try to get the shell open up a little bit earlier for y'all. But then my plan is to do a review on Monday. And so let's go ahead and put that on. So we'll do review on Monday. And so if you have any questions for the exam, you can also ask me by email so I can be sure to cover them. And then, of course, you can watch the video later. And then Wednesday, I'll probably still stream, but I'm not sure that I'll have anything prepared. But just I'll be available for questions. And again, just ask questions. I've kind of gotten caught up on grading, so that's good. And people are doing a really excellent job, so keep up the good work. Really good work on those lab reports. So overall, pretty pleased with the class. So excellent job there. All right, so let's go talk about polar molecules then. So we have to determine what is a polar molecule. And so a polar molecule is any molecule with a net dipole Now, what does this mean, though? So we said it has a net dipole moment. And well, let's kind of examine the steps that we have to go through to examine whether a molecule has a net dipole moment. So the first question that we have to ask is the bond polar? So we can start by examining each individual bond. And so let's do that with this molecule. And so we'll start off relatively simple. So this is methane. And quick review, right? Tetrahedral geometry. So just keep that in mind. That's important. And so we're looking. And so if we examine our bond, so we have a CH bond there. So that's not very polar. So we can go back to our electronegativity chart, assuming that I can find it. Here it is. And so let's see the difference between our carbon and hydrogen. So 2.55 minus 2.1. And so that falls right in the non-polar range. So right, you see it's right on the line of pure covalent versus polar. And so I would consider that still a pretty non-polar bond. But then in addition, so we said we have to analyze our bonds. So first of all, I would say this is not a polar bond. But now let's take a look at a different molecule. So now what if we look at carbon tetrachloride? So this used to be used as a solvent commonly, but it is carcinogenic, so it's kind of been phased out. And let me put our electrons in for completion's sake. And so examining this bond, so now we have a more polar bond, and we can double check that with kind of our graph here. So we have 3.16 minus 2.55. And so, right, that's showing us, so now a little bit more polar. And kind of write these elements so we can see like a hydrogen bounded with nitrogen, oxygen, fluorine. That's going to be extremely polar. And then again, right, thinking of our periodic trends where we said that fluorine was kind of our most electronegative. It's over here in this corner. So all these other elements are fairly electronegative. So that kind of gives us a sense of what's going to be polar. So anything with oxygen, chlorine, nitrogen for sure, we can see chlorine's pretty polar. And so now, okay, well, we said our individual bond is polar, but now we have to determine, well, is there a net dipole? And so basically, does the pull of the electrons, does it cancel out? And so how I suggest you determine the net dipole. So there's a couple of different tricks. So we could start off, and if you've taken physics, can be helpful, not necessary. But what you do in physics is kind of this vector addition. And so in chemistry, we draw our arrows are pointing towards a more electronegative element. And then so we can do that all the way around. And this is where, again, your molecule kit might be useful. So we have, right, we're thinking of a tetrahedral geometry, but if it's fully symmetric, so this is fully symmetric, it's going out in all four directions. And so in this case, right, we actually do not have a net dipole moment since it's canceled out. And so if we do, so let's write, so this would be nonpolar. This carbon tetrachloride is still nonpolar. But now let's compare that to dichloromethane. So dichloro means two chlorines, and then our methanes or hydrogens. And so now if we're examining this molecule, well, now we can say, right, our carbon-chlorine bonds are polar. And so let's go ahead and draw our dipole moments there. And so now we can see our arrows are just on one side of our molecule. And trying to see if trying to and so sorry, trying to show here. I don't know why I just don't have a straight red. Here we go. And so what I'm trying to show with this, if I flip back to my webcam. And so now with this molecule, we can see the unevenness a little better. So again, right, this bottom half corresponding to our chlorines, so that has a larger area of electron density. Again, the electrons are being pulled towards the chlorines. And then so that leaves our hydrogens, which I didn't put anything on there. But again, this would now be our area of just less electron densities, so we don't have, right, any electrons on that side. So we can see our unevenness. And so then we would say this molecule does have a net dipole moment. And so it would be polar. All right, let's try a little tricky one. And so this is almost a warm up too. So see if you can draw out your structure for CO. So like we were doing earlier, so how many bonds does it have? And then see if you can explore the formal charges, because this is kind of interesting. And so I'll keep it moving, but if you needed to pause and take more time, definitely do so. So let's start off with our total electron count. So we have 4 from carbon, 6 from oxygen, so 10. And so now let's see what structures you might have written. So this is where class is useful, but that's fine. We can figure it out. So we can start. What if we just draw a single bond here? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so what I'm trying to emphasize is we don't have to just know what the structure is. So we can start with this structure and let's analyze it. What's wrong? How can we fix it? And the first thing that jumps out at me is that we only have 4 electrons here for carbon. And so when you have this situation, I might suggest trying to make a double bond. And so I'm showing kind of my arrow recommendations. And so, we see that we want to follow our movement of electrons. So we circle our 2 electrons and then show them moving into a bonding. And so now I'll just rewrite this structure. And again, this is just a starting point. You could have a different and correct structure. And so now let's see where we're at. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we still have 10 total electrons. That's good. Carbon is still deficient, right? So it only has 6 total. Oxygen's happy. And so let's maybe draw another structure. So what if we try to make another bond? How does that compare? And so now we might have something like this. So again, we're trying to analyze what's our best structure. And let's see, I didn't put any formal charges. So let's go back and look at all our formal charges because this is a good comparison. So this probably not a great structure since carbon is way too electron deficient. We can still do our formal charges. So we said we start with our valence electrons, so 4 in carbon, minus number of bonds, so 4 minus 1 minus 2. So that gives us a 1 plus charge. Again, we ideally want to just minimize our charges, whatever that looks like. So not sure how I feel about that. Now oxygen 6 minus 1, 2, 3, 4, 5, 6 minus 1 bond. So that's a -1. And at least the negative charge is on the oxygen, but I still don't like that carbon only has 4 electrons. So that's kind of sad. So now let's analyze this structure. So 1, 2, 3, 4, 5, 6. So now we have 6 electrons for carbon. Formal charge, so 4 minus 2 minus 2. That gives us 0 for carbon. And oxygen, so 6 valence electrons minus 1, 2, 3, 4 minus 2 bonds. So that's both 0. And so, at least, and this is the advantage of this structure, at least we've minimized our formal charges. And so let's look at the formal charges on this CO structure. And so we look at this, let's look at our electrons. So 1, 2, 3, 4, 5, 6, 7, 8. So yay, we have 8 electrons for carbon finally, and oxygen still has 8. So that's happy. And what's our formal charge though? So we have 4 minus 3 bonds minus our 2 electrons. So that gives us a -1 charge. And then oxygen, so 6 minus 2 minus 3 gives us a +1 charge. So does anyone find anything kind of funny about that? What's kind of off? And so you may remember and kind of notice, we said that it's best to have the negative charge on the most electronegative elements except in this case, right, oxygen is more electronegative than carbon, but oxygen is carrying the positive sign and carbon is carrying the negative. So this doesn't seem right, but actually this is kind of interesting. And so it turns out this is the best representation of CO. And if you look online, so first of all, you'll get a bunch of different answers as to whether CO is polar or not. And well, I would still consider it polar. But here's where people get this kind of non-polar argument and why I wanted to at least discuss it. And so the argument is, okay, you draw this structure, you get your formal charges, and then you have a plus charge on oxygen and a negative charge on carbon. And then they say, well, you know, oxygen is more electronegative, so it cancels out. And I don't really agree with that. And so we have to think about its reactivity instead. But that's just kind of a simplistic argument, is that people will say, oh, well, the electronegativity and these formal charges kind of cancel out. And so that gives us a nonpolar molecule. Except, so let's take a deeper dive into this, because it's always interesting. And so in some ways, this assumption maybe could be somewhat correct here. So this is our dipole moment. And so I just went to Wikipedia. So Wikipedia usually has these dipole moments. You can see they agreed with us on our Lewis dot structure. And so to kind of give a range, 0, and this is referring back to polarity, but 0 would be nonpolar. And actually, let's pull up methane. So methane. And so if you recall, we said methane was nonpolar, and let's see if it has its dipole moment. So dipole moment 0. So again, just kind of putting it in context for y'all. So let's see if we can find dichloromethane and see what its dipole moment was. So remember, it was this molecule, and we said it was polar, right? Because it has those 2 chlorines, which were pretty electronegative. And don't let me down. So dipole moment 1.6. So that's kind of gives you at least a slight sense maybe of our dipole moments. And let me show you, just for reference, another one. Oh, misspelled that. So acetonitrile. Oh, let me look for the Wikipedia page. So acetonitrile is fairly polar. And so acetonitrile has this nitrogen group just on one side, and then all this are carbons. So you can see the structure here. And let's look at its dipole moment. So its dipole moment is almost 4. And so again, just kind of trying to put it in context for y'all. So that, again, that dipole moment is related to polarity. And so if you kind of wanted to check your thinking, like, am I on the right track? If this is polar, nonpolar, you can always kind of look up the dipole moment. All right, so back to CO. So we were saying, okay, well, CO might actually be kind of nonpolar-ish. But let's also take a look at what this is also telling us. So, because this is really cool, this Lewis dot structure. And this is kind of the power of these Lewis dot structures. Even though they're relatively simple, we can come to a lot of conclusions. And so with that, we find that CO can act as what's called a ligand, which basically means it can bind to metals. And what's also interesting is that it binds at the carbon. So this is again reflective of this Lewis dot structure that we determined. And so, right, we have this negative charge on this carbon and these 2 electrons here. And that's exactly what they do, is those 2 electrons come, and I'm using this arrow notation to show that there are actually 2 electrons being donated to nickel. And so I'm just drawing out, I kind of did that, a poor tetrahedral structure, but I just drew out one example. So this is nickel, uh, sorry, totally blank. So tetra carbon monoxide nickel, or sorry, nickel tetracarbonyl is the proper name. Totally blank today. So nickel tetracarbonyl, this is actually a fairly toxic compound. And so in reality, you would actually not want to work with this nickel tetracarbonyl. So it is toxic. And so what's kind of cool and toxic about this is it's a colorless liquid that produces a vapor, and that vapor is really, really dense. And it is pretty dense that a normal fume hood can't take care of it. So maybe I've seen, those things in chem labs with a big fume hood. And so those are always sucking in air, right? Except so the nickel tetracarbonyl, it can still escape from the fume hood because it's so dense. And then the other issue is, so if you were to inhale nickel tetracarbonyl, that nickel would disassociate from these carbonyls and deposit nickel in your lungs, which is toxic. And of course, the CO is also toxic. So not a great compound. Although it depends what you're going for. All right, so let's look at some other molecules and see if they are polar or nonpolar. So try NH3 for a second. And so you may remember ammonia from Monday. And so it looks something like this. So this is an interesting one. So in this case, right, all these bonds are relatively nonpolar, but we have this lone pair. And so this lone pair is an area of high electron density. And so this has a dipole moment then towards those electrons. So ammonia is polar. So same thing for water. So I'll go ahead and draw that structure out. And again, we can see how we have these lone pairs on one side kind of causing that unevenness. So let's try these two. So let's kind of compare them. And so I'll do FS6 again, sulfur hexafluoride, versus is sulfur tetrafluoride. So I'll draw it out for you. What do we think about those two structures? So polar, non-polar, what are we thinking? So if we look at SF6, so this is another one where it's fully symmetric. So if we were to draw out all our arrows, so they're all going out in an even direction and they cancel out. So this would be non-polar. And so you want to make sure that you can go ahead and draw this Lewis dot structure on your own. I kind of drew it out for y'all to show you so you could compare more readily. But again, just practice, practice, practice drawing your Lewis dot structures, your molecules. But in this case, we once again have our lone pair. And so that creates our dipole moment. So this one would be polar. Any questions about those? So I'm going to pull up another kind of reference. So I'll probably post this for the class, but this is a nice kind of reference sheet. And one way that you can use this to kind of help you is that, so if you look at this, so this key here is basically how many things are attached to it. So it calls it electron pairs, but this could be lone pairs or atoms. And so this is our big number here. And so the first one then is always going to be your fully symmetric case. So assuming, right, that these two atoms are the same, or at least relatively close in electronegativity, then of course, if you have, let's just do an example of group 2. So that would be this beryllium dichloride here. And so this, again, fully symmetric. So our chlorines would be pulling out on either side. So cancels out to nonpolar. And so again, versus if we break that symmetry, so now this would be polar. And so again, anything fully symmetric on this the first one, that's always a hint. So with this one, we could pick BF3. So BF3 or BCl3, boron trichloride. Either one of those. And so again, we said yesterday this was a trigonal planar molecule, right? Boron doesn't have any lone pairs. And so once again, it's fully symmetric and nonpolar. And then any deviations from that fully symmetric are likely polar. So now looking at this bent one, so that might remind us of the SO2 from yesterday or Monday. Sorry, I'm going to keep saying yesterday. So SO2 looks something like this. And it has that lone pair. And again, we broke that symmetry. And so that's also telling us that it's polar. And so we can see how that's kind of repeated. So now with our 4 electron pairs, we have our tetrahedral. So again, just thinking back to methane. So methane would be fully symmetric versus our dichloromethane, where there were 2 different atoms. And then again, breaking that symmetry like with ammonia or water. So that all means that it's polar. Same thing with 5 electron pairs, right? We can think of PCl5. That would be nonpolar versus any other deviation like SF4. So that would be polar, and any of these as well. And same thing applies for our octahedral geometry. We saw SF6 in this case. And so again, fully symmetric versus any other deviations. I think I'll try to post this on your notes to try to help you as another reference sheet. So how are we feeling? Any questions so far? So definitely ask questions, get help. And so now let's look at our organic structures again. We kind of touched on it briefly, and now we want to look at it again. So, right, each point here is a carbon, and then we said that carbon needs 4 bonds. And so if it's missing a bond, right, we add hydrogen. So add H to fill to 4 bonds, essentially. So I picked some fun molecules. So again, right, chemistry is always drug the class. And see if you can figure out the formula for THC here. So we want to write it out. So C something, H blah. So count up, right? How many carbons, how many hydrogens, how many oxygens. And at least the oxygens are explicitly drawn. So I'll give people a moment to do that. So while y'all are still working on that, I'm just going to draw in our carbons and try to label our hydrogens to help while you work through this. And notice they at least drew these 2 hydrogens explicitly. So they don't always do that for every hydrogen. And I'm just counting our carbons and how many things it's bonded to. Like in this case, 1, 2, 3. So I know it needs 1. I'll just continue that. So now I'm going to start counting our carbons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Uh-oh. I feel like I messed up. Let me try this again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Okay, I feel better about that one. And so you might want to mark them off or something as you count them. As you can see, it's pretty easy to lose track in these organic structures. So count and double count. And so now let's do our hydrogens. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. Oh, it's supposed to be 30, and I think I missed one. I'm going to see if I didn't fail to draw one. I could have miscounted. I'm going to try that again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 24 plus 6 gives us to 30. I think I finally counted right. So H30 And now the last one. So the heteroatoms are easier, so are oxygen. So O2 there. And so again, right, count, double count, easy to lose count. So try it again with amphetamine. So I'll give everyone a moment. All right, so hopefully this one will be easier to count. And so this is an aromatic ring here. So similar to our benzene ring. So this is benzene, C6H6. And so now let's count. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And now hydrogen. So each one of these carbons has a hydrogen, except this one, since it already has 4 bonds. So 1, 2, 3, 4, 5, then 6, 7. Don't forget this hydrogen here, 8, 9, 10, 11, 12, 13. And again, just appreciate how the hydrogens on the nitrogen are explicitly drawn. So that's always the case. So it's only the carbons where they don't always draw them out. And sometimes they do. Not really like a rhyme or reason. Questions about this? We're feeling okay about interpreting these structures. So again, I feel pretty good about things overall. And there haven't been too many questions, so I think that's always a good sign. The only thing that I want to re-emphasize is the lab. I think I pulled up the wrong lab. I believe it's this one. If I can find it. So just minor comments about this. So just make sure that, right, everything is adding up. And so you want to base it off whatever they have here already filled in. So if your mass number is 21, well, we have our atomic number. So, right, protons would be 10. And then that makes it 11 neutrons. And so just simple things like that, making sure things add up appropriately, but not too many issues on this. But the isotope calculation, this still has been an issue for students, I'm noticing. So people still have the erroneous sig figs. So I wasn't going to do it again. I think I covered it last week in lecture on Wednesday. And if people want me to find the exact video, I can do that. But I just want to emphasize, so what you're supposed to do is, right, you do the multiplication first. So you're multiplying the mass by the percent abundance. So you convert this percent to a decimal. And then you have to take into account, right, the sig fig rules. So in this case, we do our multiplication, and then we can only report the 3 sig figs on both our answers. Then we have to do the proper addition. So same thing with this one. So the flame test went pretty well. The post lab. This one has also been getting people because of this percent abundance of 1.4%. So make sure you move the decimal over twice. So it should be 0.014 when you go to multiply it. And again, you just need to take into account your sig figs. Other than that, that's about the only recurring issues I've been noticing with the lab. But sig figs are tricky, so it's always a practice. Any other? Oh, let me bring up one other question if I can find it. Because I think the other question that a few people had problems with, maybe it was lab 4, but it was something like write a formula for an ion, or for a compound with an X1 plus Y3 minus or something like that. Does that sound familiar? And so this, right, we just have to treat like our regular formula writing problems. So our ionic formulas. So remember, we're just trying to make our overall compound neutral. And the analogy I gave to somebody was you kind of think about it like Lego blocks. If the math isn't working out for you, at least mentally, because again, easiest way to solve the algebra is just swap the numbers for our swap trick. We get x3, y. But if you're a visual person, I would kind of say, right, we need to make our Lego bricks add up. So that'd be like saying our x is 1 long, and then our y is 3 long. And so how many x and y do we need? And so right in this case, so we can maybe more easily see, oh, right, each x is only 1, so I'm going to need 3 of them. So now we need 3x to match our 1y. Does that maybe help a little bit? Trying to pull up the actual lab. I'm not just... There we go. And the next problem, so we'll just review it. So it said write our formula for our X3 and Y2 ions. Again, for me, the swap trick is the easiest, but I'll kind of do this visual representation. So right, if our X is 3 long, and well, let's go ahead and swap it. So we can swap it and tell. We have 2 X's, 3 Y's. And let's now write that. So two X's that are 3 long. And then we said, well, we need 3 Y's. And so that's going to look like that. So there's 1 Y, 2 Y, 3 Y. So again, if they were Lego bricks, we would see how they would match up and line up properly. And that gives us our formula. So again, this is just a visual representation of the algebra. That kind of at least helps people make sense. And we can write it in other ways. So, right, if we say x2, well, that means I have two x3 plus compounds. And then our y2, so we said we had 3. And again, we can imagine our y2 with the relevance being that their charges cancel out. So we have a total of 6 plus charge from our x, and then 2 times 3 gives us -6 for our y there. So hopefully that kind of helps with the lab and maybe helps solidify the concept of writing our ionic formulas. And so that's just good practice to do. So again, make sure you're comfortable with naming ionic and covalent compounds. And then I will work to open up the exam week ASAP for y'all so you can start looking through that. Again, review on Monday. So if you can come live, that'd be great. So you can ask questions. If not, email me questions so I can cover them. All right. So I think I'll end my official spiel there for now. And I'll hang around on stream in case there are any other questions. And of course, email me. That's always the best way to reach me. I'm happy to set up in-person meetings or Zoom meetings. Oh, and just a reminder, today is Clubs Fair Day. So you can head on over to the Riverside campus from noon to 2 and check that out if you're interested in checking out our clubs. Don't forget Earth Club. You can join Earth Club, which I'm the advisor for. All right. Thanks again. So I will hang around on stream for a little bit just in case there are questions. Otherwise, have a great day.